Welcome to Chapter 7. Chapters 7 and 8 are going to deal with rotational motion. This is probably the single hardest part of this course, or so most students feel. So bear with me if you need to go slower. You will find that we keep re-invoking what we learned in the linear 1 and 2 dimensional systems and use analogies to understand the rotational motion. So you need to be well versed with everything we have learned so far, really master that in order to move forward, okay? So first, just like we did with linear motion, we're going to simply concentrate on describing the motion, which means the kinematics of the motion. If you try to recall, what were the 3 physical quantities that we defined in order to describe the motion, which was linear motion? We used displacement, velocity, and acceleration. And you will find that we use the same 3 quantities, but now defined in terms of angular motion, where an angle is changing per unit time. Yeah? So here are 3 quantities: displacement, velocity, acceleration, and their angular counterparts. When something rotates, it changes an angle. Imagine a circle, and one spoke is rotating around. If you define, let's say, the horizontal axis as the x-axis, then with respect to that, you can measure where your spoke is in time with some angle theta, yeah, or change an angle delta theta. So that's effectively our angular displacement now. The rate of change of this angle with time is going to give us an angular velocity, which we will label as omega, and the rate of change of omega with time is going to give us our angular acceleration, which is alpha. These are the linear quantities, and these are the analogous angular or rotational quantities. So sometimes we'll refer to these as angular quantities, sometimes we'll refer to them as rotational quantities. It's the same. It can be done either way, okay? So you need to understand this equivalence. When we're looking at angles, there are 2 units we use to measure angles. One is radians and the other is degrees. And if you're using your calculator, it can work in either mode. So you need to be familiar how to change the mode of your calculator and how to ascertain whether you are in degree mode or you're in radian mode. If you don't know how to do this, you are going to get completely incorrect answers, okay? So if you go around a circle once, you are going 2 pi radians, yes? Or 360 degrees. So 360 degrees is equivalent to 2 pi radians. Yeah? So 1 radian is equal to 360 degrees divided by 2 pi, which is about 57.3 degrees, okay? That's how you convert between radians and degrees. Similarly, if you wanted to convert from degree to radians, then we can cancel with the 2s. You can get pi over 180 times theta in degrees is going to give you theta in radians. We'll do some examples. You need to be very well conversant with how to go back and forth between degrees and radians. And you should have some sense of how many degrees makes 1 radian so that you can check your answers for correctness, right? So it's good to remember roughly 57 degrees makes 1 radian. Okay. So if we're going to measure angular displacement, let's say we have this CD and it rotates round, okay? If you're looking at some point P, you need a reference from which to define its displacement with respect to time. So typically we're going to take this horizontal x-axis as our reference axis, and we're going to center our origin on the axis of symmetry of the rotation, yeah? Or the rotation axis, which goes right through this center here, perpendicular to the disk. Yeah? So out of this page, for example, in this case, if it's rotating in this plane of projection, then the axis of rotation is perpendicular to it. On the axis of rotation, there is never any motion. Yeah? So whenever there's rotation, you want to ask yourself, where is my axis of rotation? Find a line along which there is no motion. That's your axis of rotation, where everything seems to be moving symmetrically about that axis. Okay, so that's one of the first things you want to do whenever you have rotation. You want to ask yourself, where is my axis, and become very comfortable with finding that axis. So here's the reference line, here's the origin. Here's my point P. At a later time, it has moved here, yeah? So what is its displacement from its original position? This is the path, the dashed line is the path that it has followed. It has rotated an angle theta with respect to this x-axis. If we measure theta in a counterclockwise direction, yeah? Clockwise would be opposite to this arrow. So this is a counterclockwise direction. So it's important to note that we're going to measure all angles and call them positive if they are measured counterclockwise, right, from the x direction. So that's its angular position. In terms of polar coordinates, this r here would give you the magnitude of the position vector of the point P, yeah, and theta would be the other value for the polar coordinate required, yeah, in radians. So typically we will be in radians when we are doing our SI units and calculations. Every point on the object will rotate rigidly. This is going to be our assumption. So we don't have any lag within the object, okay? And no parts of the object fall off or move at a different rate. So the entire object goes through the same number of angles in the same amount of time, okay? That's our rigid body. Okay, so now if we consider some initial position at an initial time, which is this position A, and the time is Ti for initial time, and it rotates over time to this final position B. So Tf is our time here, final time. What is the change in our position vector? Here we have, it's at the same radial distance, so our r is the same for this point and this point, but the theta is different. Theta is theta initial and then theta final, both measured counterclockwise from the positive x direction. So my displacement is delta theta, which is theta final minus theta initial, right? So this is how we're going to define our displacement, which is the angular displacement of that point. And we're going to do both of these theta final and initial in radians, okay? Then we're next going to come to the angular average speed. Okay, we're going to call that omega average, and that's rate of change of theta with time, right? Or just open both out from final minus initial. So theta f minus theta I, tf minus ti. This is our definition for angular speed, okay? And its unit is going to be in radians because theta is radians per second, right? So since time is always positive, if theta is positive, that means it's counterclockwise rotation, we're going to get omega as positive. Whereas if theta is changing in a negative fashion, so it's clockwise rotation, then we are going to get omega as negative. So omega positive or negative tells us the direction of rotation, whether it's counterclockwise or clockwise. Yeah? Okay. Let's look at angular acceleration now. Angular acceleration, alpha. You do need to memorize omega and alpha and recognize the symbols, learn to write them. Okay, we use a lot of Greek symbols in physics. This is convention, this is the tradition. You will have to use exactly the same symbols. Okay, so alpha is angular acceleration, which is the rate of change of velocity with time. So delta omega over delta t, rate of change of angular velocity with time, yeah? And we just expanded out final minus initial, like we always do, okay? So what would be the units here? We would have radians per second at the top divided by seconds, so radians per second squared, yeah? Exactly analogous to how we used to have units in the linear system. Linear acceleration would be meters per second squared. That's our displacement unit per second squared. Okay. So positive angular accelerations are counterclockwise in direction, and negative accelerations are clockwise in direction. Yeah? By the same argument that we made earlier for angular speed or angular velocity. When a rigid object rotates about a fixed axis, every portion of the object has the same angular speed and the same angular acceleration because of our definition of what a rigid object is. However, we also have a linear speed, which is a tangential speed. Okay, so these two terms are interchangeable, linear or tangential. And that speed and that acceleration will depend on the distance from a given point to the axis of rotation. Let's look at this. So instantaneous acceleration will be defined as the limit of the average acceleration in the interval delta t tends to 0. Yeah, just like we did for the linear case. Let me go back and just explain one thing to you, which was tangential and linear acceleration. So if we look at this, I told you this is our axis of rotation perpendicular going through the origin. Yeah. If you consider this point here, which we did earlier, right? It's moving at a certain linear acceleration, okay? And if you consider a point out here, okay, in line with this and in line with this, then you can clearly see that let's call that A prime and B prime. Then the points that are on the rim have to cover a greater distance, right? 2 pi r, where r is greater here, it's all the way out to the edge of the disk, right? So let's call that r prime. So 2 pi r prime is greater than this 2 pi r here, right? Fraction of 2 pi r. Fraction of 2 pi r prime here. So this point out here, A prime has to travel a greater distance because it's on the outer edge. Just like when you have a race, and if you're on the outer circle, you have to cover a greater distance if you don't go all the way around the circle. Yeah? And compared to this point here, which is closer to the axis of rotation, but they have to do that in the same amount of time because the angular change is the same in the given time, yeah? Because it's a rigid body. So that means the linear velocity here, distance divided by time, must be faster than here. And here it must be faster than when you come closer in towards the axis of rotation, because this is a shorter distance still to be covered in the same time. And as you come right to the axis of rotation, there is no distance at all that needs to be covered in the given time. So your point is stationary. Yeah? So we go from being stationary, zero linear velocity, to a greater and greater linear velocity or tangential velocity at the rim of the object. Okay. Okay. So let's do a simple problem on this. Let's say a person decides to use a microwave oven to reheat some lunch. There's their lunch, he's reheating it. In the process, a fly accidentally flies into the microwave and lands on the outer edge of the rotating plate. There it is. And remains there. If the plate has a radius of 0.15 meters and rotates at 6 RPM, that means revolutions per minute, calculate the total distance traveled by the fly during a 2-minute cooking period. Ignore startup and slow down times. So we're going to assume that the minute it starts at this rate, which is 6 rotations per minute. So we have 6 revolutions per minute. And how many minutes do we have? We multiply that by our number of minutes, which is 2. So we are doing 12 revolutions, right? And what distance is covered in 12 revolutions? Yeah. So in 1 revolution, we cover 2 pi r, where r is the radius, right, there, which is given as 0.15 meters. And we need to multiply that by 12, since we are doing 12 revolutions. This is going to tell you the total distance that the fly travels, because the fly is on the outer edge, right? So that's 24 times pi times 0.15, and that should give you your answer. Okay, so we're just going to look at that. Here we have it. Okay, 24 times pi is the angle, and then we're going to multiply by r. So 24 times pi times r is going to give you about 11 meters.